Alright, this video is going to be a short introduction to the three-dimensional space for calculus. If you're here, I imagine you're familiar with the two-dimensional Euclidean space, and we're going to use those ideas, build on them to get to define the 3D space correctly. So imagine you're trying to tell somebody how to find something on the floor in a certain room, right? That's how you use the Euclidean plane for. So if you have x and y, and you tell somebody, oh, maybe you walk 3 feet this way and maybe 2 feet this way, and then there's your object on the floor, on the ground. But what you see on the left there, right, if this gray sort of plane on the left represents the floor of your room, and we have point 3 here, 3 in x, 2 in y, and your object is on the floor, you can sort of follow these two directions and represent your object this way, and the person that you're trying to tell where to find the object will be able to find it. So that is enough to represent something that's on the floor. However, if the object is not on the floor, maybe it's, I don't know, like a fly, like flying through the room like so, then you also have to tell this person how high up it is, you know? So if you're, let's say the fly is right here, you know, 2 little wings. I have to tell this person maybe how high up above that point on the floor your object is, right? So you need to tell this person another number. You need to tell this person the x direction number, which would be this 3, the y direction number, which will be this 2, and also the z direction, how far off the ground your fly is, right? So from my picture, I try to make this a 4, like so, right? So the position of this fly right here could be represented by the 3 numbers, x equals 3, y is 2, and z is 4, like so. So this would be the position of my little fly at that moment while it flies through the room, right? So you go 3 in the x direction, 2 in the y direction, and 4 in the z direction. So you can see we need 3 numbers to do that, okay? And this is why space is said to have dimension 3, and this is why I'm going to call this the 3-dimensional space, okay? I also use the expression Euclidean, right? Euclidean 3D space, because there are certain spaces where obvious geometric facts that we expect to be true are not. Sort of basic facts about lines, planes. So as long as your objects in space obey Euclidean rules and basic geometry, as you know from high school and stuff, we're going to use this expression. But if I drop it right in this class, you generally in calculus don't go over non-Euclidean geometry, but it exists, right? Non-Euclidean geometry exists, and sometimes people are going to have to be more specific and use these words, say Euclidean or non-Euclidean. For us here, though, things are always going to be Euclidean, so it's okay to drop the word Euclidean and just say 3-dimensional space, 3D space. Okay. Now these things that we're dealing with here have names, just like in the 2-dimensional space. So we use this symbol to refer to the plane R2 to say that the thing has dimension 2, and so we're going to use the symbol R3. So R, just like for the real numbers, and a little 3 as the exponent to represent that it has dimension 3, meaning we need 3 real numbers to locate points. And we're also going to name the 3 axes. So this is the x-axis, this is the y-axis, and this blue is the z-axis, okay? So these names are important for you to remember, but they're not, I don't think, very difficult to remember because they work just like they do in 2D, in 2 dimensions. All right, So let me erase this picture here, or maybe let me see if I have space here at the bottom. So no, let me erase the fly, and I'll solve this problem here on this coordinate system that I already have, so I don't have to create another one. So let's solve this problem together. Example here is asking us to graph these points, to sketch or plot these points. Sometimes I'll use plot as well. It's fine. So the point 3, -1, 0, where's that supposed to be? That means x equals 3. So I start here at 3 on x here. Then, so here's x equals 3. Y equals -1, so I'm going to be moving that way now, right? So on the ground, I'd be sort of to the back here. But that's not point A yet. Well, actually it is, right? Because A does not lift off the ground. So point A is right here on the ground, on the floor in my room, okay? B is 3, -1, 4. So it has the same x and y coordinates as A, but then it goes 4 units up. So it's going to move up from this position until it's more or less at the exact same height as 4, not more or less exactly at the same height as 4, but in my picture it's going to be a little hard to graph this accurately. Sometimes what people do is they draw this sort of solid to represent that. And to do that, I wouldn't connect B directly to the axis. I had to do something parallel here, and you can imagine sort of a box. This sort of weird shape. It's less than, I'm not doing a great job at drawing this, I don't think, but which is partially why I wanted to have the axes already drawn. But I imagine you can see, right, this sort of box here, right? And that sort of helps if you're good at drawing, but most of the time, just to save on time and space, and also to not pollute my drawing too much, I'll just do this. And just lift it up and just connect it straight to the number 4, like so. Okay? Just do sort of the shadow that the point would have, and then connect the rest. And C is the point -2, -5, -4. So I need to be at -2 on x. So I go this way now. I'm going to go orange. -5 on y. So all the way over there. So if I follow the y-axis and the x-axis on the floor first, they're going to meet on the ground here on the floor right there. And then now I have to go -4 down. So this has got to go down on the back. It's really hard to be able to follow these correctly. And it sort of has to go down there, and that would be point C, sort of below the ground, below the floor of this room that I'm imagining here, okay? So you should practice doing these yourself, okay? If you don't have the axes, I generally just do this. I just do this. It's going to be Z, and then X, Y. You should be able to do this yourself most of the time, okay? They should be at 90 degrees. But because of perspective, sometimes it doesn't look like so. This angle here in the middle especially may look like it's not 90, but it's just perspective. But I'm not drawing the 90 degrees. Again, this point here in the middle is called the origin. And it has coordinate 0, 0, 0. All 3 coordinates are called 0, 0, 0. All 3 coordinates are 0. Right, so the coordinates of the point are 0, 0, 0. And just like 0, 0 in R2, right, was also the origin. We use the letter O, so we save O for that point. Another important part of the Euclidean space are the coordinate planes. So back in R2, in 2 dimensions, you only had the coordinate axes. You had the x-axis and the y-axis. So in dimension 3, you have 3 coordinate axes this time. So you have the x-axis, the y-axis, the z-axis like you've seen. But here in 3D, you also have coordinate planes, right? Because space is three-dimensional, two-dimensional things fit into the space. And so if you imagine, again, this is like a corner of a room or something like that, one of the walls is going to be a plane that's important, a coordinate plane, okay? This plane right here does not move away in the x-axis. Do you see that? It doesn't leave the x-axis. If you look at the x-coordinate of any of the points on this wall, on this blue wall, it's going to be 0 because it doesn't move this direction or in this direction. So all the coordinates of this point have x equals 0, right? And so this is called the yz plane. Meaning x equals 0, it's irrelevant. You don't write it when naming the plane, right? So this is the yz plane. So it has equation x equals 0, okay? Now on this one, there's no y coordinates here, meaning all y coordinates of the points on this other wall, this blue wall here, they are 0, the y coordinates of these. So this guy will have equation y equals 0. And this is called the xz plane. Again, y is 0, so why say it, right? You just say the x and the z. And lastly, you have when z equals 0, which would be the floor, the ground in your room, right? The room you're imagining. Whenever the z coordinate equals 0, that means you don't have any height to the points you're talking about. So this is called the xy plane. So z is 0, don't say it. Okay? You have to be able to talk about these planes as they are given right now. One thing that happens, I don't have a computer generated picture for this, is remember in R2 how you had the x and the y axes, and those divided the plane into 4 parts. You had the first quadrant, the second quadrant, and this is the third quadrant. And the fourth quadrant. And so sometimes you say Q1, Q2. I usually see it in Roman numerals like this, but I've seen it with regular Indo-Arabic numerals too. This is in R2, right, with dimension 2 in the plane. But in R3, things are a bit more complicated, because if you imagine all of those 3 planes at once, right? If you imagine all of those 3 planes at once, you can imagine this. There's this sort of on the back, and everything above that. There's this and everything above, this and everything above, and this and everything above. So that's already 4 parts. And then you have the parts below them too. So if you go below the floor, there's one part here, and then one below the floor there, and one below the floor there. So you have 8 parts that your space is divided into. So maybe if I sketch this slightly differently here again, you can imagine, a wall like this, another wall like this. So you have 2 walls sort of meeting at a corner. And when I dash my lines like this, I'm trying to say that this is behind. So this dashed line is being shown behind the one that's solid. So I hope this picture is good enough for you to tell that there are 2 walls meeting at a corner, like so. And like I said, you can see these two walls forming these sort of four different rooms. There's this, there's this, there's this right here, and there's this right here in front, right? So there's definitely four different rooms. But then you have the below and the above, right? You have the below and the above. And so there's eight of them, right? There's eight, and you don't call quadrants anymore. You call them octants because there's eight of them, right? For obvious reasons. So let me also draw the ground a little bit. I'll try my best. It's kind of hard to do. But I'll draw the floor, the ground, that being the other plane. But what I want first from you is that you see, maybe if you want to draw yourself at home, that'd be better, to make you see the octants. And now I want to start naming them, okay? So maybe this line is here. So above the x-axis, above the xy plane, above the ground, you have four octants, okay? Oh, four octants. And they're named just as they're named here. So you have positive x and y giving you first quadrant. So positive x and y will give you first octant. So that will be octant 1. You have here in front the first octant. And then what I imagine is you're looking from above, like this. A bird's eye view of this should correspond to that, because this is the x and this is the y plane axis, x and y axes. So this is the first octant. This would be the second octant for positive y, right? Positive y. And this on the back would be the third octant, and this here will be the fourth octant. All with positive z coordinates. And then if you go below, then you're going to get, you go in the same direction now, and then you're going to get the fifth octant on the back here. Fifth octant. And then below on the back, you get the sixth octant. Here you get the seventh octant. And here below this one, am I saying this? Let me look at this again. No, I started wrong from below, because it got to be below the first, right? So here you have the fifth octant, and below the second you have the sixth octant. Below the third, right, you have the seventh octant, just add 4, and then below this one you have the eighth octant. Okay, this is kind of complicated. I can see if I can find a different picture to show you what's going on, but the idea is clear. There are 8 parts. This is the takeaway from this. Most calculus teachers won't ask you to think too much about this, but I just wanted to show you just in case. All right, another important thing from the basics of the 3D space is being able to orient your axes correctly. Sometimes the shapes that we have, as you can see by my suffering, by trying to display and represent the octants, sometimes the shapes that you graph or that you plot are in a weird octant for you to graph this way. So you have to sort of rotate. Imagine the room that you're looking at has an object behind a table or something, and then you got to walk around and look at it from the other angle to be able to see it. If you go and take a picture of that room now, on that picture, the x, the y, and the z axis, they're going to be in different positions. And so you have to make sure that you didn't mess up the geometry of the space when you moved. Of course, in a room, you won't do that, but in your graph, since you're the one labeling, you may happen to label things incorrectly. And also, Because we're going to be doing calculus in 3D, right? We're going to be solving calculus problems. You have to watch that whatever you're doing doesn't generate weird areas. Can you imagine solving an integral for an area? And that's an integral, blah, 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 blah. And at the end, you get a negative number. -5 or something. That can't happen, right? Areas have to be positive, lengths have to be positive, volumes have to be positive. And so in order for that to happen, your three axes have to be oriented correctly. This is called positive orientation. It's called positive orientation. Positive because of this, right? The correct integrals give you positive area. This is arbitrary. We could have chosen X, Y, Z to be in different positions, but we chose this one, and now everybody has to follow this choice just because if we choose it differently, we have to change all of our formulas for areas and volumes to make sure that the answers are positive. Okay, so this is just arbitrary. It's just a choice. And for it to be positive, it has to obey, the three axes have to obey and follow what's called the right-hand rule. Now, I got this picture here from the Wikipedia Commons, so it's a free picture, no copyright. And how does the right-hand rule work? You have to imagine that your thumb on your right hand, right? So start with your right hand, of course. Your thumb pointing towards the z-axis like so. And you should be able to, with your index finger, point towards the x-axis. So that's sort of a first check, right? And if you were to curl your index finger towards, to the direction of the palm of your hand, then that should be pointing towards the y-axis. In this picture, you see your middle finger pointing towards the y-axis, and that's fine too. But I've seen people able to at least partially put their middle finger towards the back of their hand, and that's not what we want. We want to be able to have the middle finger pointing towards the face of their hand like this, or away from the face of their hand like this, right? In the direction of the face of the hand and not on the direction of the back of their hand, which is why I like to say that you're curling your fingers at times. Curling the index finger towards the middle finger should go from X to Y. It's alphabetically, right? X to Y. So for you, I'm going to do an example of this before next. And for you to be able to do this, you have to pause, actually get your right hand out, and actually try and do the things I'm describing. Okay, so let's go. Here's an example. Which of the following coordinate systems have positive orientation? Okay. I'm not going to try and draw a hand too much here. Maybe I won't resist. But here's the point. See that the X and the Y and the Z axis are not in their standard position on item A there. If you put your thumb pointing this way and your index finger pointing this way, right? That would be curling your index finger towards the face of your hand, the palm of your hand, from Y to Z, not from X to Y, right? If you also put your thumb this way and your index finger this way, so this being your thumb right here, and this your index finger, which is longer this way, you would be able, with your right hand, to curl downward and not upward, right? Towards the face, towards the palm of your hand. So that does not agree with the y-axis that we have on the screen. So that is not positive orientation. It does not obey the right-hand rule. Now for B. Thumb on the z-axis, index finger of right hand on, so this should be your thumb, and your index finger towards the x-axis. If you curl your index finger in, right, towards the palm of your hand, you'll be curling it that way. And that's not the positive direction of the y-axis, right? So that's also not positive orientation. Okay? C, thumb towards the z-axis, index finger towards the x-axis on your right hand. So actually pause the video, position your hand this way, right? Imagine a corner of a room in front of you. And can you curl your finger, your index finger, towards the y-axis, right? So that it goes towards the middle finger that's already sort of curled in. Yes, you can curl your finger this way, right? So that would be, yes, positive orientation. And finally, if you have thumb towards the z-axis, index finger towards the x-axis on your right hand, when you curl it in towards the palm of your hand, you'd be curling it backwards this way, right? So that would be also not positive orientation. We always want positive orientation, so if you see on an exam or something, a picture such as this one, that'll be fine. Yeah, it's as though you're in the correct room, right, that we're describing before where the fly is flying. And maybe you're taking a picture and this is the floor. Yeah, this is the floor. Just taking a picture from a different angle instead of taking the picture from like a standard angle that you started with before. But the other ones that are in red, they're not correct positive orientation. Sometimes it's beneficial to work with these. We're not going to do that in calculus. And these red ones, they're called obviously negative orientation, but we're not going to be dealing with them too much.